you will definitely come across, if you haven't already, the facility location problem. And the only question that I have is whether you'll recognize when you see it. So you'll definitely come across the problem. It just might manifest in a way that you may not recognize it to be a facility location problem. As it happened with me, so 7 or 8 or 9 years ago, when I was working on that particular problem, and I didn't recognize that this was actually some form of facility location problem, even if not exactly. So since we have seen many different applications, let's try to create a mathematical model, and this is one of the many different models possible. So we can talk about this problem in a more mathematical setting in terms of algorithms and lower bounds and things like that. So here's a mathematical model. So we might be given a weighted, strongly connected graph. So it's strongly connected, and each vertex is a client. The client has some demand. So demand can be talking about how much of the goods are required from the warehouse by each store, or it could be how much of the data is required by that node if it's a communication network. So the distance can be modeled as the weights on the edges. So if it's a mathematical graph, then we can put the distance on or any form of transportation cost on that particular edge. For example, if it's a highway or it's a small network, then we can maybe able to cost the model either the fuel price, the fuel cost, or the time, or maybe a combination as each edge. Similarly, the demand can be modeled as the weights on each vertex. And now the question that we have is, we can place the facilities at any of the k vertices within our graph. So if we can imagine that all of our facilities will be co-located with so the warehouses will be co-located with some of the stores. They'll be quite near the stores, so then we just have to select the k vertices from the graph, which will then serve all the other clients. Does that make sense? So that's our question here. So one specific question can be, at which vertices do we place our k facilities so that we minimize the maximum distance for any client. So from any client, you should be able to get to a facility close by within the time that's not too long. Now it's possible that we may not want that, we may want something different, and we will see those variations as well. But does this problem overall make sense? Okay. And here's a quick example. You can see if these are the if this is the graph that's given to us. Right now we're not really worrying about the actual values, just looking at a figurative sense. So if we have two facilities to place, where would we place it? Likely not here and here, right? Maybe somewhere closer towards the center, but we don't know that yet. So we want to minimize the distance to each client to its closest facility, right? So we want to minimize. So this is also called the minimax problem. So you're trying to minimize the maximum distance over all vertices to their closest facility. And it's possible that this could become that these two places, which are this node here and this node here, could become the facilities that we are referring to. And this particular problem is called the k-center problem. The facility location problem is just a general problem. Depending upon what actual mathematical model we choose, it will have a different name and an actual different mathematical problem underlying it. And this specific problem is called the k-center problem. We'll cover it again in a minute. But the question that we're trying to answer is, how did we choose these locations without testing all of these choose and k combinations? So if we had to use choose and k combinations, then it would be considered an exponential time algorithm, right? Is that part clear? What would be the choose and k value? What is an approximation of choose and k? What's an approximation? What's the value of choose and k? What's the formula for that? So it's n factorial by k factorial divided by n minus k factorial, right? So how would we approximate that? you can tell any larger number than that, and that would be fine. Okay, I see some people trying to work out, so I'll give you a minute.
Any larger number?
Any upper bound on that, so we can just have it.
Factorial?
Sorry?
And factorial?
And factorial would be fine, though I'm hoping if we can have a number that's not as bad as that. That's still is a closer approximation. Jared, do you have an answer? I guess we could write it this way. We could write the choose nk as n minus 1 and minus k plus 1 divided by 1 to up till k. Is that a fair representation of choose nk?
Can you use a bigger?
Yeah, I think we should. So is it a fair representation of choose nk? Just n factorial divided by, just wrote it down. So this is, we can say, is about, there are k terms here, right? So it's about n power k divided by something. So we can say it's order of n power k. All of these terms are less than equal to n in the k terms, right? And I choose to just ignore the denominator for now. So this is order n power k. So why do we call this an exponential time? It looks like polynomial in a way. We call this exponential time because k is an input. K is not 3 or 4. If k was 3 or 4, then we would have called it a polynomial time algorithm. Here k is an input because the question was, we're given n and we're given k, and what's the highest that the k could be?
Whatever the problem says.
Whatever the problem says, but let's say if k was as high as n by 2, then this would become n power n by 2, as high as that. We should not say that k can be as high as n, because if that's the case, then the problem becomes very simple. You just allocate a facility at each location, but the maximize, it becomes a maximum when the k is n by 2. So that's when this combination choose nk is the highest if k is n by 2. So in that case, so that's why we call this exponential time. So this problem's lower bound, or the problem hardness, seems quite high, right? So let's talk about the problem hardness for a second. But I would like to first of all point out that the real world problems don't necessarily have lower bounds or NP completeness results or things like that. It's their mathematical models that have that. And obviously this slide took me a little longer to make compared to the other slides. But thanks to the advances in the computer science and in the technology that anybody can now go and make a cartoon, it doesn't take all that long. So if we try to enforce an answer on a real world problem, then the conversation can kind of look like that. So that's not what we